My name is K. Veeraswamy, Senior Lecturer, Government Polytechnic Nirmal. Department Electrical Electronic Engineering. I am teaching third semester subject DC machines and batteries. The main topic DC motors, and subtopics working principle of DC motor. So after completion of this period, you can able to explain DC machine as a generator in motor, Fleming's left hand rule, working principle, introduction. Although a generator a greater percentage of electric machines in service are AC motors, the DC motors of considerable industrial importance. The principal advantage of a DC motor is its adaptability to different methods of speed control to provide a wide range of speeds and good speed regulation. Right? So very important thing is greater percentage of electric machines are actually AC motors, and the DC motor. The DC motors of considerable industrial importance. So because of the principle of advantages of a DC motor is its adaptability to different methods of speed control. Very easy to control the speed of DC motors when compared to the AC motors. So very easy, very smooth variation of speed control can be obtained by using these DC motors. A machine that converts electrical energy into mechanical energy is known as a DC motor. Next, a DC machine as a generator and a motor. A DC machine is manufactured or purchased. It can be used both as a DC generator and as well as a DC motor. Only electrical machines provide this kind of wonderful facility. That is, if electrical power is given input, it gives mechanical power and is called as a motor. If mechanical power is given input, it gives electrical power output and is called as a DC generator. DC machine is manufactured or purchased. It can be used both as a DC generator as well as a DC motor. Only electrical machines provide this kind of wonderful facility. That is, if electrical power is given, it gives a mechanical power and is called as a motor. If mechanical power is given to its electrical power, it is called a DC generator. So you can observe. So DC generator means here mechanical energy given to DC generator, the output mechanical energy converted into mechanical energy. Before going to working principle of DC motor, you must know what is Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. The direction of force acting on a current carrying conductor can be determined by Fleming's left hand rule. This rule is applicable only when the conductor is at right angles to magnetic field and is stated as: place the left hand, forefinger, middle finger and thumb mutually perpendicular to each other such that the forefinger in the direction of the current and thumb represents the direction of the motion of the conductor. Right? This is known as Fleming's left hand rule. So this is the basic principle for a DC motor. Fleming's left hand rule. By stretching or place the left hand, forefinger, middle finger, thumb mutually perpendicular to each other such that the forefinger pointing the direction of the magnetic flux and the middle finger pointing the direction of the current and the thumb representing the direction of the motion of the conductor. So you can observe, very simple. Your left hand, thumb in the direction of the motion of the conductor, and this shows direction of the magnetic field, and this shows the direction of induced EMF, right? That is current direction, magnetic field direction. Then the thumb shows the direction of the motion of the conductor. If you step the right hand such that, so pointing finger in the direction of magnetic field and middle finger in the direction of the current, then the thumb shows the direction of the motion of the conductor, that is the motor direction. Motor direction. Suppose let us consider this one. So this is North Pole and represent dot. Dot means current enters. This is magnetic field direction, North Pole, north to south magnetic field, and this shows the current and this shows the motion of the conductor. If this is the current, okay, and this is the direction of the, so this shows the current out of the board, right? You can observe, and this shows motion or force, right? So this is Fleming's left hand rule. So this is a magnetic field direction, and dot means this is the direction of current direction, right? You can observe, this is a magnetic field and this shows the current and this shows the motion of the conductor, motion of the conductor. So in this way we can find the direction of motion of the conductor by using Fleming's left hand rule. The Fleming's left hand rule is used to determine the direction of the motion of the conductor which is placed in a uniform magnetic field. When a current carrying conductor Fleming's left hand rule, Fleming's left hand rule, right? So by stretching left hand of forefinger pointing in the direction of the magnetic field and middle finger in the direction of the current and the thumb show the direction of the motion of the conductor or force direction. You can observe this is a field and current, the thumb force. The y-axis represents the force direction. The force experienced by a current carrying conductor. So this rule is applicable to electrical motors and measuring instruments, and this rule can be represented as forefinger F flux, its unit is Webers, middle finger, middle letter I, first letter force, we can represent flux. In middle finger MI is middle I represents current. The thumb, thumb capital M shows motion for motion of the conductor, right? This is the basic principle behind in the DC motor, right? So very important thing is DC motor can be operated as generator and a rotor. That means by giving a mechanical energy to DC generator to the DC machine, it gives an electrical energy. Then that machine is known as DC generator. Suppose if you give electrical energy, then if you get to an electric DC machine, suppose if you get a mechanical energy, then it is called a DC motor. Right? So the DC motor, today our topic is working principle of DC motor. So DC motor means by stretching our left hand such that pointing finger in the direction of the magnetic field, thumb in the current, and in the direction of the middle finger pointing the middle finger in the direction of the current, and this in the direction of magnetic flux. Thumb shows the direction of motion of the conductor. Next, working of a DC motor. Basically, there is no construction difference between a DC generator and DC motor. In fact, the same DC machine can be used as a generator as a motor. So motors are classified in the same fashion as a DC generator according to field winding connection like shunt, series and compound motors. Consider a current carrying conductor placed in a magnetic field. Assuming the current flowing in the conductor is away from the observer shown by the cross, establish a magnetic flux around the conductor. Right? Here observe a current carrying conductor in a magnetic field, and current enters into the board or away from the observer. That's why it enters. That's why it is represented by cross. Generally, it is represented by arrow tip. Suppose towards observer, towards me, then I can observe only tip of the arrow. So it is a dot. If it enter into the board, into the paper, or away from the observer, it is represented by cross. Right? Next, how to find the direction of magnetic field. So let us consider a current carrying conductor. Consider current carrying conductor placed in a magnetic field, and this shows the direction of the current, and the remaining four fingers shows the direction of magnetic field, So right hand rule, holding a conductor in your right hand and thumb in the direction of the current, and remaining four fingers gives the direction of the magnetic field, So by using this principle, we can find the direction of the magnetic field. Suppose here consider a current is dot. A dot is represented means, suppose in this direction current is towards me, right? So the cross means current is away from the observer, right? This is away and towards me, right? So towards me means I can observe the tip, that's why it is represented by dot, right? So hold the conductor, right? Holding the conductor, and this is, and thumb in the direction of the current in minus direction, dot means in my direction. So by holding a conductor, this conductor, you can observe in the diagram, and the thumb shows the direction of the current, and remaining four fingers shows the of the magnetic field or magnetic flux, direction of field or magnetic flux, right? So we are consider only conductor. Suppose if it is a cross, right? You know that in one conductor, if the top conductor is a cross, the same current one is enters means it must leave to another side. So if it's a coil, the current enters into the coil, means represent the cross, and again it passes to the second side of the conductor and leaves means a dot, cross and dot. Suppose it is a cross, suppose if it is a dot, and how to find the direction of the magnetic field, right? So again, holding the conductor in your right hand such that current in the direction of, thumb in the direction of the current. So here a cross means into, right? So into in this direction current away from me, and the remaining four fingers you can observe in the diagram. This is the direction of the, that means a clockwise direction. Clockwise direction is the magnetic flux direction, right? And one more thing is, and from north to south, again there is a magnetic field. So the straight line represents main magnetic field direction, right? And this, when current passes through the armature conductors, right, and it produces a magnetic field, right? Produce a magnetic field or magnetic flux around the conductor, right? So in this way you can find direction. Suppose and armature magnetic flux, main magnetic flux and armature magnetic flux. If you observe one side, on one side of the magnetic pole, what happens, right? Current, if it is clockwise direction, the main field flux and armature flux both are in the same direction at one tip of the north side. Suppose if you in the diagram north pole, left side and right side. Observe the left side and right side. On one side, armature flux added to the main flux, and one side armature flux is opposite to the main flux is in this direction. Right? Armature flux is in the counterclockwise direction and clockwise direction. So this side, on one side, so the armature flux adds to the main flux, and another side armature flux opposite to the main flux, right? So therefore, so magnetic flux decreases on left side, magnetic flux increases on right side. So you can observe in the diagram. So observe. So this side, one side, the flux decreases, another side flux increases. The distortion of the flux will take place. The bending of the flux will take place, right? So when current passes through the coil, when the flux weakens the main flux on the left side of the one side, left side, and strengthened on the right side, right? The main flux, the flux on right side of the conductor, so the flux concentrated on right side of the conductor pushes the conductor towards the left side, towards the left, with a force F is equal to BIL, right? You know that it pushes the flux, the concentration of the flux, one side flux increases, this flux pushes the conductor to one side, that is the left side, with a force F is equal to BIL newtons, right? So because of that, magnetic lines of force moves always in a straight line. Why? Because the magnetic lines of force always moves in a straight line, right? Because of the current in the conductor, the magnetic flux decreases on one side, increases on one side. That means because of what happens, the bending of the magnetic flux will take place. But what is the main property of the magnetic lines? Means magnetic lines is always flows in straight, but there is a opposition, there is an obstacle between the flow, main flow. What is that? Conductor. Because of that conductor, flux is bending. Suppose if there is no conductor, then automatically lines become straight. So the increase in flux moves the conductor to left side. It moves the conductor with a force F is equal to BIL. Then the lines becomes straight. Right? So the working principle of a DC motor can also be understood by considering the part of a multipolar DC motor as shown in the figure. Conductor, right? Suppose the cross conductor, on top there is a cross conductor and the bottom there is a dot conductor. So the cross conductor moves the conductor armature on left side. Similarly, below conductor moves on right side, right? Then automatically we get a twisting force. If you consider two conductors, we have considered only one conductor, but actually two conductors. Upper one becomes cross, another one becomes dot. If a cross means the force in this direction, dot means force in this direction. So there is equal and opposite forces acting on opposite side. So simply we get a rotating torque. So again I will explain with multi poles. The working principle of a DC motor can be understood by considering a part of the multipolar DC motor as shown in the figure 3.2. When the terminals of a DC motors are connected to a DC supply source, when the terminals of a DC motors are connected to the DC supply source, First one, the field magnets are excited and developing a alternate north and south poles, right? When a DC supply is given, what happens? The field magnets are excited and developing a alternate north and south pole. Number two, the armature conductors carry current. North pole and another one is a south pole, right? And and then current passes through the conductor. So the conductor and the north pole is a cross, and the conductor and the south pole is a dot. You can observe the dot and cross represents armature current, right? And same time, when current passes the field winding, it will produce two north poles, north pole and south pole, right? Next, armature conductor and north poles are assumed to carry the current away from the observer shown by the cross, and those of under south pole to carry the current towards the observer shown dot, right? So applying Fleming's left hand rule, then the direction of the force on each conductor can be found, right? So by using Fleming's left hand rule, right? So let us consider only cross conductors, right? So this is a magnetic field direction, north pole, right? And the current is cross, it is into the board. Sorry, left hand, I am taking right hand, sorry. This is magnetic field direction, and this shows the current into the board, into the paper, right? And this finger shows the thumb. You can observe in the diagram. So my thumb shows the direction of the motion of the conductor, right? The force. So that's why it is in this direction. It is an anti-clockwise direction, right? In this way. Always magnetic lines enters into the south pole. So this is the direction of magnetic field. It is a dot. Dot means this one. Dot. Right? And this shows conductor motion. Again clockwise. So simple. So the cross and dot conductors moves the conductors in anti-clockwise direction. The conductors under north pole moves in clockwise direction, and at the same time the dot conductor on south pole also moves in the same clockwise direction. So automatically we get a twisting torque and the rotor rotates, right? Small arrows on each conductor, it will be seen that each conductor experiences a force of waves which tend to rotate the armature in anti-clockwise direction. So these forces collectively produce a driving torque which sets the armature rotating. Right? Very simple thing is, so working principle of induction motor, DC motor can be explained in two ways. That is simply by using a property of magnetic lines, and second one is by using Faraday's law of Fleming's left hand rule. By using two rules, so we can understand the working principle of DC motor, right? So the operation of DC motor is based on the principle that when a current carrying conductor is placed in a magnetic field, a conductor experiences a mechanical force. And the direction of this force is given by Fleming's left hand rule. The direction of this force newtons. B is the flux density in the Tesla. I is the current in the amperes. L is the conductor length in meters. Right? So that is the force acting on the conductor when it is placed in a magnetic field, right? So we know that when a current carrying conductor is placed in a magnetic field, it experiences a force. That force is given F is equal BIL newtons, where F is a force in newtons, B is the flux in the Tesla, I is the current in the ampere, L is the conductor length in the motor, right? Flux density in the Tesla, B is equal flux density in the Tesla, and I is the current in amperes, and L is the conductor length in meters, right? Next, back EMF. When the armature of a DC motor rotates, the conductor also rotates in the magnetic field. So according to Faraday's law of electromagnetic induction, EMF is induced in the conductor whose direction, as found by Fleming's right hand rule, its direction is found by Fleming's right hand rule. So it is in opposite to the applied voltage, which is shown in figure, right? Because of this opposing direction, it is referred to as a back EMF EB. Obviously, V has a drive IA against the opposing EMF EB, right? So once again I will explain how a back EMF is developed, right? So let us consider here. So there is a magnetic that dot, right? So if it is a dot, say a magnetic field, it is a dot, and this shows the direction of the motion of the current. In the previous case, we consider as under north pole a cross, then we get in this direction. Suppose if we consider dot, we get in this direction, right? So next, what is the back EMF, right? So you know that Faraday's law, according to Faraday's law, whenever a current carrying conductors or simply a conductor cuts a magnetic field, an EMF is induced, right? Here two things are happen when magnetic flux cuts the conductors. Here current carrying conductors cuts the magnetic field. What happens? Simply according to Fleming's left hand rule, a force act on that when current carrying conductor placed in a magnetic field, a force act on that. Because of that force, it rotates in clockwise and anti-clockwise. At the same time, the conductor cuts the magnetic field, an EMF is induced. Already there is a one EMF, so it is flowing into the board or out of the board. It is a dot or crash. Suppose you assume that dot is in my side, right? So this is the one case. Simply we are providing the current, we are applying a voltage. Because of that armature voltage, the current will circulate. That current is an armature current. This dot represents the armature current, right? In this same conductor, right? So because of the cutting of the flux to this armature conductors, voltage current will circulate because armature current will flows, and this is the current, right? But according to Faraday's law, there is another EMF is induced in the rotor conductors, That EMF is known as a back EMF. Right? Why it flows in opposite direction? Right? Here the flux, because of cutting off the flux, EMF is induced. Right? So to according to Lenz's law, the induced EMF flows in such a way that it opposes the cause. Right? Here, because of the current flowing in a conductor, we get a magnetic field. So this magnetic field cuts the armature conductor. Right? You observe. So this is a dot. Similarly, in a dot. So because of that, we get a magnetic field. That is a dot. In this direction, magnetic field flows. Right? So this magnetic field, observed in the diagram, this magnetic field cuts the conductors. Right? What happens? Then EMF is induced in that. The EMF is induced That's why it is called a back EMF. Why? Because according to Lenz's law, the induced EMF is always flows in a such a direction it opposes the cause. Here the cause is because of this clockwise flux, armature. Because of armature flux, EMF is induced in. Okay. So to oppose that, the current flows in opposite direction. If is this in a dot, then current enters into the board. Then what happens? The current will be, the magnetic will be in anti-clockwise direction. Sorry, clockwise direction. So because of back EMF, we get a clockwise flux. Because of supply voltage, we get a clockwise flux. So these two are equal and opposite. Right? The back EMF will produce the flux opposite to the armature flux. Opposite to the armature flux according to the Lenz's law. According to Lenz's law. Right? So that's why this EMF is known as back EMF. That's why this EMF is known as back EMF. Clear? Right? When the armature of a DC motor rotates, the conductor also rotates in the magnetic field. According to Faraday's law of electromagnetic induction, EMF is induced in the conductors, whose direction is found by Fleming's right hand rule in opposition to the applied voltage. In opposition to the applied in opposition to the applied voltage as shown in the figure. Because of the opposing direction, it is referred to as a back EMF. Is referred to as back EMF, right? So in this case, here we consider V as the supply voltage. V as the supply voltage. Because of supply voltage, we are getting armature current. Because of armature current, we get a magnetic flux. Because of the observed in the diagram. So V is in downward direction, EB in upward direction. It is always opposite to the supply voltage. Always to the supply voltage, right? So it is given, armature current is given by V minus EB by RA, net voltage by resistance. So the resultant current passing through the armature winding is given by I is equal to V minus EB. Actually, we applied a V. So minus EB. EB is a back EMF developed in the armature conductors, right? Because of the flux cut by the conductors. The conductor cuts the flux. So because of that, EMF is induced. That EMF you have to subtract that, which is opposite to the supply voltage. So V minus EB, that is a net flux or net voltage by resistance RA. So this is known as armature current. Armature current. So resultant current passing through the armature winding, where RA is the armature current, where RA is a armature current. Again, so the formula for back EMF is given, induced EMF or back EMF is given by EB is equal to phi Zn by 60 into P by A, where phi is the flux, Z is the number of conductors, N is the speed, R is a constant value, and P by A, P is number of parallel paths, so number of poles is parallel paths, right? So this back EMF depends upon armature speed. Back EMF depends upon armature speed. If speed is high, back EMF is high, and hence IA is small, and hence IA is small. If speed is less, EB is less, and hence more current flows to develop a torque. Right? So this back EMF is directly proportional to speed. That means at starting, when speed is equal to 0, when speed is equal to 0, back EMF is equal to change in flux. That flux, if the conductor is stationary, right, there is no change in flux. If it rotates, then only EMF is induced. So because of speed only, we are getting a back EMF. E is equal to phi Zn by 60 into P by A, where phi is the flux, main flux, and Z is the number of conductors, and N is the speed, and 60 is a constant one, and P by A, P is the number of poles, A is a parallel path. P is how many number of poles are there, and number of conductors, and speed, A is the number of parallel paths. A is equal to 2, and A is equal to P. A is equal to P for lap winding, A is equal to 2 for wave winding. So this back EMF is depends upon armature speed. If speed is equal to high, back EMF is high, and hence I is small. If speed is equal to less, back EMF is less, and hence more current flows to develop a torque. Right? So this is about back EMF. This is about back EMF. Then formula for back EMF for different DC motors. Right? Suppose for a DC shunt motor is different and DC series motor is different. So let us consider general equation E is equal 5Zn by 16 P by A. In a DC motor also, the EMF is induced in the same way, but it is opposite to the supply voltage. Hence, it is known as a back EMF, and it is given by the formula E is equal 5Zn by 16 P by A. So V minus Ia into Ra for a DC shunt motor, and V minus Ia into Ra plus Rac for DC series motor. Right? Back EMF is equal V minus Ia Ra for DC shunt motor. So V minus Ia into Ra plus Rac for DC series. When current carrying current according to Faraday's law of electromagnetic induction, then EMF is induced in the rotor conductors, right? The induced EMF because always flows opposite to the supply voltage. So next and very important thing is, what is the significance of back EMF? Suppose when there is no back EMF, what happens, right? Actually at starting, when back EMF is 0, right? Suppose when back EMF is very less, we know that armature current, the armature winding is very less, very small, right? At starting, what happens? It draws very high current. Armature draws very high. So armature current is given by V by Ra. Ra is very small, right? The running condition, when this motor started, what happens? Back EMF is developed. That back EMF opposes the extra current. It opposes the supply voltage V minus EB by A. So net voltage decreases, right? So simply, when back EMF is 0, current increases. When back EMF is increases, current decreases, or for a required level. Otherwise, we get a very high current. Simply it acts as a governor. It acts as a governor, right? So when back EMF increases and decreases, right? Depends upon the speed. Right? So this is a significance of back EMF, right? And next, last and most important one is classification of DC motors. DC motors are usually classified based on the field winding. So that is, DC motors are classified into separately excited DC motor, self-excited DC motor. Again, self-excited DC motors are two types: shunt, series, and compound. And again, compound motors are short shunt compound motor, long shunt compound motor. Short shunt and long shunt compound motor, right? It depends upon the generators or motors classification. Both are same, right? Only these are classified according to based on excitation given to the motor. Excitation nothing but by giving the supply. This is to the field winding, right? And armature winding, separate separate excitation, separate voltage is given to the field winding, then is called separately excited. Self-excited means some part of the current uses by this DC motor, that is a shunt motor, series motor, compound motor. That means the field winding is connected parallel to the armature winding, that is called shunt motor. If the field winding and armature windings are connected in series, that is called a series motor. In compound motor, shunt and series, both the field windings exist, shunt field winding and series field winding. So again, we have two types in the compound: shunt compound motor and long shunt short shunt and long shunt. If the shunt is short is known as short shunt. If the shunt is long is known as long shunt compound motor. Long shunt compound motor. Summary. So today we discuss 4 important things. So first one is introduction. So that means a DC machine can be converted into generator or motor. By giving a DC supply, we get a mechanical energy, so it is a DC motor. By giving mechanical input, we get electrical output, that is known as the same machine can be used for generation only, generation of energy. So one machine DC machine can be used as a generator and motor, right? And again the DC motor right hand, left hand, so pointing finger in the direction of magnetic field, middle finger in the direction of the current, and thumb shows the direction of the motion of the conductor. That is, when current carrying conductor is placed in a magnetic field, it experiences a force. That is the working principle of a DC motor, right? So DC motor working principle can be explained in 2 ways: by using properties of a magnetic lines, or by using Fleming's left hand rule. And next one, third important one, is significance of back EMF. The back EMF is developed opposite to the supply voltage. Why? Because the armature conductor is rotating in a magnetic field. When a conductor is rotating in a magnetic field, means it cuts the magnetic field and there is a change in magnetic field, so the EMF is induced in the conductors, right? That induced EMF is always opposite to the supply voltage. That's what is known as back EMF. That what is known as back EMF. When back EMF is depends upon speed. When speed is equal to 0, back EMF is 0. When speed increases, back EMF increases. Back EMF increases. And last one is different types of DC motor. Separately excited DC motor, self-excited. Self-excited shunt, series, compound. Again, compounds are short shunt and long shunt. Short shunt and long shunt. Thank you very much.